Greetings and welcome to Chapter 5, Section 4, Indefinite Integrals and the Net Change Theorem. I'm going to be talking through some slides that were provided for Stewart's Calculus Early Transcendentals 8th edition, and at the end of these slides I'm going to toggle over and look at a homework assignment that I have given to my own college students, and I will work through some of those problems and talk through some of those problems, and we'll see some already worked out example problems in the following slides provided by Stewart. And I will do my best to connect some topics and theories, and also, of course, talk about some of the processes used to solve these problems. This is another set of slides that I'm going to talk through where there are really more slides than I feel like we need to address. So some of them I'll be breezing through, and if you want to pause and have a look at them and see if the language in the slides jives with you, then great. Otherwise, the way that I'm describing it might work well for you, and of course you might need to be tapping into your own resources, other videos, your textbook, etc. So indefinite integrals, this slide's also referencing the fundamental theorem of calculus, FTC2. There are two halves or parts to the fundamental theorem. Indefinite integrals are integrals where we are, or where you end up with a formula or an equation, and you don't end up with a specific value. And the indefinite integral could end up being created by doing integration that looks like you're striving for a definite integral, but with that x value in there as your upper limit, you will indeed end up with an indefinite integral or a new function or equation. And we've seen this previously as the process for finding the value of a definite integral. Lowercase f is the given function in here, and then when we see the capital F here, that is the antiderivative. So this is a recap of something that we know already, that the integral of lowercase f equals a new function, capital F, and inversely, if you then took the derivative of capital F, it would lead you back to the original function, lowercase f. And then here's an example. We've taken x squared, we've integrated it, we've gotten this family of functions, x to the third over 3 plus an unknown constant value. And then if we were to take the derivative of that new function, we would end up with the original expression x squared again. We should distinguish carefully between definite and indefinite integrals. That's true. One you end up with a function, the other one you end up with a number. Fabulous. I'm not seeing any limits of integration here, so that tells me I'm going to be looking for an indefinite integral. And we're going to review a table briefly, and as you know, I don't memorize. It's not that I don't memorize anything, it's that some things stick and some things don't. Some things I think should be memorized, some things shouldn't. So I've actually printed out the table of integrals that we're going to be looking at on your screen in a moment, and I'm going to be referencing that table. Here, however, we're being reminded that the integral of secant squared of x is equal to the tangent of x, and if we took the derivative of tan x plus our constant value, of course, we would end up back at secant. And remember that the argument of an integral function is called the, oh, that's not true. The output, rather, of the integration process is the integrand. Differentiating the function on the right-hand side and obtaining the, I lied. It's the argument. The argument of the integral function or integration process is called the integrand. So sloppy. Integrand. I keep reaching up to my laptop and trying to scroll through these slides, but they're not up there. They're down here on my iPad. Here's the table that I was mentioning. I take like 3 or 4 days off from making videos, and all of a sudden I can't function anymore, apparently. Sorry about that. So here's the table that I was mentioning, the one that I printed out and held up in front of the camera a second ago. And some of the ones that I struggle with are secant squared integrating back to tangent, and cosecant squared going to negative cotan. What's another tricky one? I don't know why I don't ever remember this. And the hyperfunctions, I didn't ever work with those. And so I'm certainly growing up and in my undergraduate and high school education, we just never worked with those functions. So I definitely never had those in my memory. Some of these, though, you're going to work with so frequently that you'll be able to come right back to them very easily. This is another one. It's just unusual. I don't think you see it very often. So anyway, I'll be coming back to this slide or just glancing down at my printout in order to reference and make sure I don't make any mistakes. So, as I've mentioned in a previous video, making sure to include plus c as a constant value is very important. And when you go through the integration process and you end up with your new expression or your new function, there's an understanding that the new function has a particular domain. So sometimes you won't see the domain written explicitly, but for example, that particular function, 1 over x, if you were going to be as thorough as possible, you would probably want to express it as a piecewise function so that the integral was defined on the portions of the real number line where the function's actually defined. So we don't want to be using an x value of 0, so we're using x values less than 0 and greater than 0. Here's another example of an indefinite integral, and this one's a little tricky. This is one of those problems where you want to do some initial work, and in this case, the factor of sine squared theta in the denominator has been broken up into 1 over sine and cosine over sine, so that 1 over sine can become cosine. Which is not true. 1 over sine does not equal cosine. 1 over sine is equal to cosecant. So that is a typo on the author's part. So this should say CSC theta. And then, now that that says cosecant times cotan, let's scroll back up. The integral of cosecant times cotan is equal to negative cosecant. Let's see if the author got that part right. Negative cosecant plus our constant value c. C, we're all human. This book has been around for quite a while, and the author is vetted, and a copy editor went through and looked at all this stuff, and undoubtedly some colleagues of his went through and looked at this stuff, and that one still slipped through. So, helps me breathe a little easier. In this example, this is a definite integral. You notice that we have our limits of integration going from 1 to 9. This is the expression that we're going to be integrating or finding the antiderivative of and then evaluating. And then here's the process written out for us. But this is another example of where there's a first step that's a good idea. I describe this process as distributing my division. So I'm going to take my first term and divide it by t squared, my second term and divide it by t squared, my third term of -1 divided by t squared, and that leads us to this new integrand. This is what we will take the antiderivative of, and when we do, we get the 2t over here. The exponent increases by 1, and we divide by the new exponent. And the same thing is happening here. This exponent's increasing by 1, and then we're dividing by that new exponent. Then you can clean things up a little bit, adjusting the signs between your terms, maybe moving the negative exponents and writing them as positive exponents. So instead of t to the negative 1 in the numerator, t to the positive 1's appearing in the denominator. And then we go through the evaluation process. Notice those same limits of integration are over here, but now those are the b and the a value that we're going to be plugging in when we evaluate f of b and f of a. Let's see that on the next slide. Here we go. This is f of b, so we're taking the 9 and plugging it into that antiderivative, and we're plugging the 1 into the antiderivative. We're subtracting or finding their difference, and then from there it's arithmetic. You've already done homework assignments where you're finding antiderivatives, and you've done homework assignment, I believe, where you have already evaluated and solved a definite integral. So there it is again in generality. Lowercase f, antiderivative, you get capital F, and then we evaluate capital F for your upper limit minus capital F evaluated for your lower limit. And unusual, I think, to see it written this way, but notice that f of x and f prime of capital f of x, those two are equivalent. So thanks to the inverse nature of derivatives and integrals, we can make that happen. And as we continue talking about applications now, so we're into slide number 2 of 11 regarding applications and not just integrals, we're being reminded that the first derivative of capital F, in other words, f prime of x, represents the rate of change of the original function, capital F of x. So derivative represents rate of change. And we say with respect to x, that's obviously our independent variable in there. And the difference between your output values is your change in your y values, essentially, as your x values move from a to b. We're right back into Algebra 1. This is y2 minus y1 and x2 minus x1. And they're highlighting, the author's highlighting something here that says that the difference between those two y values essentially represents a net change. So we do a little bit of reformulating the second portion of the fundamental theorem of calculus, and we can say that we have a new theorem, the Net Change Theorem, whereby if you integrate, you're essentially finding a difference between y values. So we have done what it looks like is happening here. We're taking the first derivative of this function just to integrate it again. Aren't those two things processes going to cancel out? Yes, except this is a definite integral, so we're not just taking the derivative and integrating and ending up right back where we started. We're taking the derivative and then integrating and then evaluating from a to b. So we end up finding a difference in y values. Why is that important? It's important because using that or those two processes, derivatives, integrals, and subtraction, I suppose, we can use those processes in order to apply calculus more easily to the social sciences, natural sciences, and other real-world events. So what we're going to do in the next handful of slides is walk through and see some of those relationships. This is a little bit challenging because we're not immediately going to work any problems. So these are going to be very generalized statements, but these are things that you could refer back to after I move through them fairly briskly. You could go back through and watch and listen and pause and write some notes down about the different relationships that we're going to see. And then when you go on and you're working your own homework assignments and you run into these types of relationships, hopefully it'll make those a little bit more easy for you. So, for starters, if capital V of t is representing the volume of water in a reservoir at time t, then the first derivative, V prime, is the rate at which water flows into the reservoir. In other words, it's the rate of change of volume of water in the reservoir. So if we integrate the derivative, remember that capital V stands for the volume in the reservoir, and V of t2 represents the volume of water in the reservoir at time 2, that's the later time, minus the volume in there at time 1, the earlier time. So what this ends up representing is a very specific change in volume. Okay, it's literally going to be whatever they're going to measure it in, cubic yards, gallons, I have no idea, but they're going to get some kind of a numerical answer, okay, that has units on it, units that measure volume. Capital C can represent concentration of a product in a chemical reaction. The derivative, C prime, which is being expressed in a way that's different than we're used to maybe, okay? So this is delta C over delta T, so that's change in concentration divided by change in time. In other words, the first derivative. And then if we integrate that first derivative, there it is, integrating it with respect to time, then we have concentration at the later time minus concentration at the earlier time, which ends up equating to change in concentration from our first time T1 to our second time T2. So there's a chemistry application that we're seeing. The mass of a rod, which doesn't seem like it would be very valuable, does it? Unless you're the manufacturer of a fishing pole, or maybe you're manufacturing parts of a crane. And so the mass of the structure of the crane as it goes farther and farther out, the weight of that extended, right, cantilevered out part of the crane, the weight of that being pushed down, we need to know what that mass is, and the mass as we go all along. So that's getting into some more particular physics problems and strength of materials kinds of issues, stuff like that. So these are real world things. These are just like little kid examples, maybe. In a way, I don't mean that to sound belittling, of course, but these are the building blocks of larger problems, to be sure. So the mass of a rod is measured from the left end point out to some other point along the rod. That mass is going to be measured or represented by the function capital M. So the linear density, which is a very problem-specific and physics-specific term, the linear density is being represented using this other function. I don't know my Greek letters exceptionally well. Some of them I do, so I don't remember what this one is, but I'm going to say P of X, which I can't believe he doesn't know that, probably. I can't know everything. So P of X is going to represent the first derivative of our mass function, and then we're going to integrate that derivative, and it takes us back to the mass function so we can find a change in mass, and what that ends up helping us determine is the mass of a segment of the rod between A units and B units out into the rod. Population again, so this is, if the rate of growth of population is this, so that's already a growth rate. We're not even being told that there's an original function lowercase n, okay? N must represent the population. It's a numerical value. And if we integrate the derivative, again, we can find, in this case, change in population. This one's actually a little bit more interesting than usual because population is certainly determined by births and deaths. So those things are happening in a way simultaneously all the time, right? So this integration process is including maybe with, if time were measured in days, of course there are births and deaths and births and deaths and births and deaths happening. And if we're only looking at maybe this portion right here, if that's that interval represents 1 day, and we were to integrate this, this would be a positive area, and this would be a negative area, and this would be a positive area, and this would be a negative area. We'd be adding all those positives and negatives together and coming out with what ends up being the net change. So if 1,000 people die and 1,001 people are born, then this integral right here is going to come out equaling 1. Okay, even though there were 2,001 events that took place. So we want to be mindful of that. We've already talked about this in a previous video, that there are times when excuse me, we want to be adding those negative areas that are below the x-axis, excuse me. And there are times when we want to be making those negative areas into a positive so that we can get a feel for the actual total amount of change that happened. Cost functions, marginal cost, we've seen this in a previous video. First derivative of cost is marginal cost, and if you integrate that, you're going to get a change in cost. We've mentioned this also in the past, that S represents a position function, V then represents a velocity, which is the first derivative of the position function, and then I'll remind you that the derivative of the velocity equation is the acceleration function. And so here we're integrating the velocity function from t1 to t2 to find a change in position. This is another example. My analogy, I think, was if I get in the car and I drive 25 miles to work and then I drive 25 miles home, if I were to integrate that on an interval that represents my entire day, my total distance traveled would end up equaling 0, because I would have some sort of positive amount of distance traveled on my way to work, and then I'd be at work, and then I would drive home, and if I find the area under this curve, it's going to end up being 0, as long as I didn't take a detour on the way to or from work. So another instance where we have to be careful of where our function resides above and below the x-axis. Displacement is a specific word that's going to represent net change of position. So in my example, my net change is actually 0. Okay? If you wanted to calculate total distance, so if I want to do 25 miles to work and 25 miles home from work, and I want to get 50 as the answer to my integral, then I'm going to need to take the absolute value of that function so that I end up with all of my areas under the curve being above the x-axis. And there it is. We're still in generality, right? We still don't have any actual numbers, but you can see that when you're looking at displacement, which would have me driving 0 miles, because I would do 25 miles to work, and then from work would end up being negative because I'm driving backwards, essentially, the opposite direction I was earlier in the day. I end up subtracting that same 25, I end up with 0. However, if we're looking for distance and we take the absolute value of this function that's in here, we end up with a plus sign instead of a minus sign, and so I would end up with my 50 miles total round trip to and from work. Here there are 3 segments, and we're seeing over here that middle area under the curve is the one that's negative, so that's why we're subtracting a sub 2. The way that this integral over here is being represented, a sub 2 is a positive area. A sub 2 as a number is positive. But because it's below the x-axis, we have this subtraction sign. So a1, a2, and a3 are all in and of themselves positive numbers. It's a question of whether we're subtracting them as we are with a2 right here, or if we're adding them with as we are with a3. And a1 you see is positive. Or what you see is that a1 doesn't have a negative sign in front of it. All right. Acceleration is the first derivative of velocity, so if you integrate acceleration, you're going to get a change in velocity. Oh my gosh, it's an example problem with numbers. It only took us 27 minutes to get here. Thanks for hanging with me. The particle moves along a line so that its velocity at time t is represented by this function as measured in meters per second. Find the displacement, and then you notice in part B it says find the distance. So displacement is going to be that net change, which means all we have to do is integrate. And in this problem, we're looking at the time period from 1 to 4 seconds. Let's see how the author in these slides lays this out for us. Remember, this one again is displacement, so all we have to do is integrate. We're integrating our function v of t. That's the eraser, that's the pen, there we go, v of t. We're substituting in v of t, that's the only thing that's changed. Here we have found the antiderivative of v of t. And you'll notice that there's a typo in this also. Wow, killing it. Pretty sure. Notice the original function is t squared minus t minus 6. If you're taking notes, this should say t squared minus t minus 6. Oh boy. There's another issue here. When we integrate t squared, increase the exponent by 1 and divide by the new exponent. This, however, this 1, which should say t, or it should say minus t instead of minus 1, when you integrate t, you should get t to the second power divided by the new exponent. So this exponent should have a 2 there, so that should say t squared over 2. And the last one, he got that one right. That is minus 6t. These are our limits of integration from 1 to 4. So you would plug the 4 into this expression first, and then plug in a 1 into the expression, subtract those two values. So again, plugging in a 4 minus plugging in a 1, and that ends up equaling negative 9/2. 4 minus 1 doesn't equal 9/2. Evaluating this expression at 4, and then evaluating that expression at 1, and then doing the subtraction, that's going to get you your answer of negative 9/2. It's so nice to not be the only one making the occasional error. And then we go to part B. So part B, remember, is where we're looking for distance traveled, which means anywhere that we had a negative velocity, because we're traveling backwards, we want to somehow squash that negative. So what is being done here, and you're going to have to do this at some point, no doubt, is the original velocity equation is being factored, t minus 3, t plus 2. This is a right side up parabola. 1, 2, 3, 1, 2. This has zeros at negative 2 and at positive 3. It's a right side up parabola. Halfway between negative 2 and positive 3 is positive 0.5. So I've got a vertex that's down here somewhere. And my parabola looks something like this. Never took an art class in my life. Isn't that amazing? You'd never guess. We're integrating from 1 to 4, don't forget. Let me switch colors here. We're integrating from 1 to 4. Ooh, I'm going to have to make that curve a little bit longer. There we go. And we're finding the area under the curve, right? Because we're integrating. Which means there's this area in here, which is negative. If we just evaluated the integral, that would end up giving us a negative result. And then there's this second area over here from 3 to 4, which would give us a positive area. So this idea of taking the absolute value of our function better is to, if you've watched any of my other videos, drawing even this really horrendous diagram can be super helpful. And of course, doing this bit of factoring over here is helpful because it helped us find our zeros. Right side up parabola, right? Because it's got a positive leading coefficient over here. That's going to help us figure out how to change the original limits of integration where we went from 1 to 4. And now we're going to instead we're going to integrate from 1 to 3, and then we're going to continue on from 3 and finish integrating up to 4. But we're going to insert this negative sign, which is effectually, it's not even a word. Effectively, it's taking the absolute value of our function on that particular interval. Remember, the absolute value takes what's negative and makes it positive. Well, that's what that little minus sign's doing there. Our velocity equation is below the x-axis right there. Our y values there are negative. Our integral would be negative. But putting in that minus sign is going to make it positive. Taking it negative and making it positive sounds like absolute value to me. This is just, we're kind of doing it manually. And only on that interval from 1 to 3. Okay, so let's see, we're integrating from 1 to 3 for the opposite of the original function. All right, so it's the opposite of our original function, so notice that this, let's go this way, this is indeed the opposite or the negation of our original velocity equation. All the signs have been changed, good. And then, so we'll do that integration momentarily, and then here we have our original function v of t, so no changes there, but we are only integrating from 3 to 4. Let's go down here. Now we're gonna end up with two different antiderivatives. Not a big difference, but a little bit of a difference. It's that negative sign that we're gonna see as being the difference. So let's double check the author's integration. Yep. Okay, don't see any typos. Great. So where I was just erasing, this integration is done, or at least the antiderivative of this expression is found, and it's in here. And then this, over here is actually just the opposite. That's a negative sign. It's the opposite of the first, the previous derivative, this one over here. Okay, they're literally opposites of each other. Why take the antiderivative twice, right? This thing is just the opposite of the stuff to the left of it. After having figured out the antiderivative, and that the second one is just the opposite of this one, we've got our antiderivatives, then we have to do our evaluation. upper limit of integration, lower limit of integration. Those two values get plugged in, right? So we've got to do capital F of 3 minus capital F of 1 to use the notation that we've been using for quite some time now, plus, and really we could be doing it this way, just in case this were a minus sign in here, it would be important to enclose this in parentheses, and here we've got F of 4 minus F of 3. Interesting. That's what's happening. Actually, this is what's happening in here. Okay, between this equal sign and this equal sign, this is what's happening. Okay, we're doing all the arithmetic, all the plugging in. What if we combined like terms right here? Isn't this f of 3 going to cancel out with this minus f of 3? So doing this symbolically, if you will, allows us to see that those two things are actually going to cancel out. So we could skip doing all of that arithmetic. All we have to do is evaluate f of 4 and then add it to the opposite of f of 1. So we need to evaluate this expression over here for 4, and then we need to evaluate this expression over here for a positive 1, and then negate it because of this minus sign right here. Don't forget that one, right? See that one there? How many times can I draw this arrow? Don't forget that minus sign. So if you got your eyes open and you're keeping your eye on the big picture, as well as the nitty-gritty of the arithmetic, and the more familiar we get with the process and the concept, you might be able to save yourself a little bit of work there. So keep an eye out for that shortcut. And that's the last slide. We moved through those pretty quickly. That was good. There wasn't a lot of arithmetic to do in this one. We're 38 minutes in, give or take. So let's switch over and have a look at some more example problems. Oh, hello. Where are those example problems? I might have to go into here. Yes. There we go. Let's zoom in a little bit. So here we're finding a general indefinite integral. You've done these already in previous assignments. Let's use this one. First step that I would recommend in this one, I'm not going to work this one all the way out. This is not complicated. What you're really integrating here is 3 times, and then I'm going to rewrite this radical expression using entirely exponential notation. So this is really x to the 3/2 power plus 8 times x to the, we're squaring it and we're cube rooting it, so it's the 2/3 power. If you want to put all that in parentheses, that's not a bad idea. You're integrating it with respect to x, and then you know what you need to do. You're going to increase this exponent by 1, and then you're going to divide the original coefficient by the new exponent. It's going to be a fraction, so you'll have to do a little keep, change, flip action there, but nothing you can't handle. Same thing's happening in that second term. Oh, it's going to show us solutions maybe. I want to turn that option off. We want to work the solutions out for ourselves sometimes. Let's take a new screenshot of that. Bunch it up, full page, zoom it in. There we go. In question number 2, find the general indefinite integral. This is another problem that we're being given just to remind us that sometimes you have to do an initial little bit of work in order to prepare before you do the integral. You want to if I can borrow my own language, distribute your division. So you want to do that division into that term, divide into this term. We want to do those two steps first before we try to integrate. So this ends up equaling the integral of, this first reduction is nice, it's 4x squared. The next one, you're subtracting 7, and then remember that x, the square root of x is the same thing as x to the 1/2 power, and this denominator is really x to the first power, so 1/2 minus 1, right? The upper exponent minus the lower exponent, 1/2 minus 1 makes negative 1/2. So we could think of this as 7 times x to the negative 1/2 dx. We use our parentheses, and when you integrate, now it's the same process. Increase the exponent by 1, divide by the new exponent. If it's fractional, keep, change, flip. Don't forget to bring the 7 and the 4 along with you. Sometimes I'm so focused on the exponent that I forget that there was an original coefficient on my term. Next one. Okay, so this one's a little bit different. This first term, very straightforward. This term, also straightforward. Pretty much, when you integrate a constant, remember that the variable is going to appear to the first power. So the integral of 5 is 5x. How can I check my work on that? Is there a way that I could know that I got that correct? Absolutely. Once you integrate, if you're not sure you did it correctly, take the derivative. See if you get your original expression back. This is where it gets weird. The integral of this is equal to the integral of 9 times 1 over x squared plus 1. Terrible handwriting, but that says x squared plus 1. We could have even taken the 9 and written it outside the integral, so that we're really focused on taking the integral of 1 over x squared. And you might be thinking to yourself, I don't know how to do that. And in a way, you're right. And the good news is, you don't have to know how to do that, because it's one of the integrals from our cheat sheet, or from our table of integrals that we saw, that some of you are going to have to memorize and some of you won't have to memorize. Depends on how your teacher or professor is running the class. Good news is I'm running this class and I say I'm not memorizing that, and so I'm just going to tell you on this one so you don't have to go look it up in case you couldn't see it when I was holding it up to the camera, that the integral of 1 over x squared plus 1 is the inverse tan of x. Tan to the negative 1, but we say inverse tan. So you do still have to find the integral of this term, or the antiderivative, and the antiderivative of this term. And the antiderivative of this last term is not just the inverse tan of x. Don't forget, we have to bring that 9 with us. See, I almost forgot the coefficient, or that constant multiple. So that's 9 times the inverse tan of x. And at the end of this problem, and at the end of this problem, and at the end of this problem, you're going to need plus c at the end. Don't forget that. And a capital C, if you don't mind. Find the general indefinite integral. Great. What's the integral of the sine function? Check your table. Okay, these are things you need to be looking up for yourself. I know what that one is. And don't forget to bring the 6 with you. Actually, that one I'm going to do because, well, this is equal to 6 times the integral of the sine of x dx, which equals 6 times, and what's the integral of the sine function? It's negative cosine. And so just the integral of this first term ends up being negative 6 cosine x. I didn't want you to end up writing it so that it looked like 6 minus cosine of x, because that's not true. And if we took the derivative of this, would we indeed get 6 sine of x? Absolutely. because the derivative of cosine is negative sine. So the negative sign and then this negative symbol, they'd cancel each other out, leaving you up here with 6 sine x. Notice that that term is positive. Where's my back button? There it is. Get rid of all that. Bye-bye. Today, please. And then there's this hypersine function. Don't know. Checking my table. The integral of hypersine, hypercosine. Plus what we said previously for the integral of 6 sine x, and what goes at the very end that you're not going to forget. These instructions are nice, man. This is reminding you, or at least they're trying to remind you, that you need to have that plus c at the end. This is an indefinite integral. This solution is actually a family of solutions because of this unknown c value. Number 5, the general indefinite integral. Check your integral table and see what is the integral of cosecant squared. Check your integral table. What's the antiderivative of e to the power of whatever? In this case, it's e to the t. On your table, it might say e to the x. On your table, it might say e to the u. U usually represents an entire expression, but we're not there yet. Don't forget the plus c. I wonder if 1 plus tan squared alpha, in this case, has a special antiderivative. Let's check our table. 1 plus tan squared. I'm looking. It's not in the first column. I'm getting excited because it must be in the second column. 1 plus tan squared. It's nowhere to be found. How am I supposed to take the integral of this? There's a couple of possibilities. One is to realize that this is equivalent to the integral of 7 d alpha plus the integral of tan squared alpha d alpha, or with respect to alpha. The integral of 7, the antiderivative of 7, I can handle that. It's going to be, I won't tell you. That one you should be able to handle on your own. What about the integral of tan squared? Maybe on my cheat sheet, there's an integral of tan squared. Let's see. Right-hand column, not there. Left-hand column, still not there. What a stupid table. So the fact that this was not helpful, I knew that it wasn't going to be helpful. You have to be even more clever than grabbing your integral table. Let's just do a quick bit of review, shall we? Sine squared theta plus cosine squared theta equals 1. That's the trigonometric Pythagorean identity. If you divide the entire equation by cosine squared, right? What I do to one side of an equation, I have to do to the other. You're in Calc 1. You know that already. And I'm distributing to my division. I'm dividing each term by cosine squared. Sine squared divided by cosine squared is tan squared, plus anything divided by itself is equal to 1, equals the reciprocal of cosine is secant squared. Ooh, tan squared minus 1, or plus 1 is equal to secant squared, which means I could take this 1 plus tan squared and replace it with a secant squared. Let's do that. This is equal to 7 times the integral of secant squared alpha with respect to alpha. Fingers crossed that secant squared is on this piece of paper. Starting on the left-hand column, it's tangent. Unbelievable, all that work just to get back to tangent. The integral of secant squared is tan. You might have known that one already. Tan goes to secant squared. In this case, we're going secant squared back to tan. And so our solution is 7 times the tangent of alpha plus c. If you don't type that in, like my students in WebAssign, you don't type in the plus c, I don't actually know what's going to happen. Maybe a face will pop up and laugh at you. I can't believe you forgot the c. We reminded you about the c right here. I don't know what's going to happen, but paper and pencil, college level, my guess is you're losing points if you don't put the plus c. Evaluate this integral. So this one is a definite integral. We have limits of integration on this one. And the integral or antiderivative of e to the x, that one you can look up. Antiderivative of sine, I think we talked about that already. Be careful with your positives and negatives. Realize that this is going to give you some new function. Let's call it f, capital F. And you're going to have to evaluate that function from 0 to pi. So when you find your antiderivatives of these two terms, when you find those two antiderivatives, this might be a plus sign between them, might be a minus sign. I'm not going to give it away. That's going to be your new function, capital F of x. And then you'll have to evaluate your new function, your antiderivative, at pi, and then evaluate it for 0, and then you'll subtract those two intermediate values or solutions. All right, and that'll take you to your final answer, the answer of your integral. It's going to be in terms of pi. You're going to have e to the pi in there, okay? And if you're using a calculator to evaluate your trig functions, pi is a radian measure. Make sure that you're in radians, please, okay? Also remember that anything to the power of 0 is equal to, do you remember? It's equal to 1. Last question, at least in my homework set. This homework set actually doesn't have any of the word problems that we were talking about previously, so I'm not stressing my students out with the word problems because at the time of this recording, we've only transitioned over to we've transitioned our in-person classes to online classes because of COVID, and so I'm trying not to have this online course be too strenuous because none of my students who are watching this video signed up to take an online class. So to try to be fair to them a little bit and give them a little bit of grace, there are no word problems in this one, but being aware of those relationships is good, which is why I wanted to talk about it earlier in the video. This problem, definitely going to need to do some preliminary work before we evaluate or take the antiderivative. My guess is that you will want to change this to 8 over cosine squared theta plus 3 cosine squared theta over cosine squared theta d theta. And then we'll do one last little bit of preliminary work before we actually take the antiderivative. What is the reciprocal of cosine? That'll be secant. That's cosine squared, so we're going to have secant squared. Don't forget the multiple of 8. You can put that multiple of 8 in here, or you can factor it out of the integral process. Just don't forget to include it, right? Bring it with you. We're actually integrating secant squared theta. We've talked about that already. Oh no, that was 1 plus tan squared that we talked about. Well, that turned into secant squared. I'll let you go back and figure it out. I'm pretty sure it was secant that we looked at before. And anything divided by itself is equal to 1, so this really just says 3. And you are still integrating with respect to theta. So again, you'll need the antiderivative of this term, the antiderivative of this term. That's going to give you your new function, capital F. Oh, sorry. I didn't actually say anything wrong, but the way that I wrote this is incorrect. This multiple of 8 that's out here actually only applies to the integral of the secant squared. So really you should close your parentheses here and then have a new integral from 0 to pi over 4 on the 3. And you could even put in a new d theta in there. That might end up looking more complicated than necessary. This statement is now correct and it's true and it is equal to the previous line worth of work. I think the better way to write it, though, at least for some of us who are not feeling exceptionally comfortable with all this material yet, let me recommend that you write it this way. I can't even slide my page up any further because I'm at the bottom of the page. Don't factor this 8 out of here. Let's leave it in there. I would write this, if you're not as comfortable as some of your peers maybe, let's write this as the integral from 0 to pi over 4 of 8 secant squared theta plus 3. That way you can put all of that in parentheses because you are going to take the antiderivative of all of that with respect to theta. Remember, theta is just a variable. It could be an x, it could be an alpha. It doesn't matter. In this case, it's a theta because we're working with trig functions. You're still going to have to integrate this constant value with respect to theta, though. It's going to be a little unusual, but not too bad. And that's going to give you your new function in terms of theta. And then you're going to have to plug in the pi over 4 and evaluate, and then subtract whatever result you get when you plug in the 0. So you'll need f of pi over 4 minus f of 0. Whew. Antiderivatives, evaluating, making sure to use parentheses when you're setting up the evaluation of these antiderivatives, right? Maybe put this stuff in parentheses and this stuff in parentheses just in case there's a sign change mixed in there somewhere, right? So be careful with that. And that's it for this section. This was really just kind of an applied section of the antiderivatives and the integrals, being mindful, again, that there are some times when you'll want to use that sort of absolute value feature when you're looking for net change, for example, in distance, as opposed to total distance traveled. That's when you're going to want to chop up the interval of integration so that you can take anything that was below the x-axis and flip it up to be above the x-axis by negating it. Okay, no negative areas. And that's it. I hope this was helpful. We're just about at the 1 hour mark, so I'm going to go and you go do some homework. Thanks for joining me, and I will see you in 5.5. Take care.